When an object falls back to Earth from space or descends through the upper atmosphere at hypersonic speed, it does not simply heat up. It enters one of the most extreme physical environments naturally produced on this planet. Temperatures can exceed 7,000 degrees Celsius. Air becomes plasma. Shockwaves compress into invisible walls of energy, and materials experience forces comparable to those inside rocket engines and stars. This process is called atmospheric re-entry, and it is one of the most violent interactions between human engineering and natural physics ever attempted. Re-entry heating is not caused by friction, as many people believe. It is caused primarily by compression. When a vehicle travels at several kilometers per second, it cannot push air molecules out of the way fast enough. Instead, air piles up in front of the object, forming a powerful bow shock. Inside this shock layer, air density increases dramatically and molecular kinetic energy converts directly into thermal energy. This compressed air becomes superheated plasma, radiating intense heat back toward the vehicle surface. This is why re-entry heating is governed by gas dynamics and thermodynamics, not surface rubbing. To understand how temperatures can reach 7,000 A circumflex degrees C, we must start with velocity. Objects re-entering from low Earth orbit typically travel at approximately 7.8 kilometers per second, or about 28,000 kilometers per hour. That corresponds to roughly Mach 23 at high altitude. At these speeds, kinetic energy is enormous. Using the kinetic energy equation, 1/2 mass times velocity squared, even a relatively small vehicle carries energy equivalent to multiple tons of TNT. That energy must go somewhere. During re-entry, much of it is transferred into the surrounding air. The temperature of compressed air at the stagnation point, the region directly in front of the vehicle, can be estimated using the stagnation temperature equation. This relates temperature rise to velocity squared. At orbital re-entry speeds, stagnation temperatures exceed 6,000 to 7,000 degrees Celsius. This is hot enough to dissociate oxygen and nitrogen molecules and strip electrons from atoms entirely. The result is ionized gas, or plasma. This plasma emits visible light, producing the glowing sheath often seen around spacecraft and hypersonic vehicles. This plasma layer creates what engineers call a communication blackout. Radio waves are absorbed or reflected by the ionized gas, preventing signals from reaching antennas. During spacecraft re-entry, this blackout can last several minutes. Hypersonic atmospheric vehicles experience similar effects, although usually for shorter durations. This is not a software problem. It is a fundamental consequence of physics. As air becomes plasma, its chemical structure changes. Oxygen molecules split into individual atoms. Nitrogen breaks apart. These atoms recombine on vehicle surfaces, releasing additional energy through exothermic reactions. This process, called catalytic heating, adds to the thermal load. At the same time, shockwave compression raises pressure dramatically. Near the stagnation point, pressures can exceed several atmospheres in milliseconds. Heat flux values can surpass 1,500 watts per square centimeter, comparable to the thermal environment inside rocket nozzles. These conditions explain why ordinary metals cannot survive re-entry. Aluminum melts at 660 A circumflex degrees C. Steel begins losing structural strength above 1,200 A circumflex degrees C. Titanium alloys weaken beyond 1,600 A circumflex degrees C. Re-entry environments exceed all of these thresholds. This is why spacecraft and hypersonic vehicles rely on specialized thermal protection systems rather than conventional materials. One of the earliest solutions was ablative heat shielding. Ablative materials are designed to slowly burn, vaporize, and peel away during re-entry. As the surface erodes, it carries heat away from the vehicle. The Apollo capsules used ablative shields composed of epoxy resins and fiberglass. As these materials decomposed, they absorbed enormous amounts of thermal energy, protecting the astronauts inside. Each mission consumed several centimeters of shield thickness. Modern systems often combine ablation with advanced ceramics. Ceramic matrix composites can survive temperatures exceeding 2,000 A circumflex degrees C while maintaining structural integrity. Carbon-carbon composites, used on spacecraft nose cones and leading edges, remain stable above 3,000 A circumflex degrees C. Ultra-high temperature ceramics such as zirconium diboride and hafnium carbide can tolerate even higher temperatures, approaching 4,000 A circumflex degrees C. These materials are among the most heat-resistant substances ever created by humans. But temperature alone is not the only challenge. Re-entry also generates massive mechanical stress. Vehicles decelerate from orbital speed to subsonic speed within minutes. This produces forces several times Earth's gravity. Structural components must endure vibration, compression, and thermal expansion simultaneously. Electronics must operate inside insulated compartments while external surfaces glow white hot. Every interface becomes a potential failure point. The shape of a re-entry vehicle is just as important as its materials. Engineers discovered early that blunt shapes are safer than sharp ones. A blunt body pushes the shockwave away from the surface, creating a thicker layer of hot air that acts as insulation. This counterintuitive design dramatically reduces heat transfer to the vehicle. Pointed shapes, while aerodynamically efficient at low speeds, place the shockwave directly on the surface, increasing heating to catastrophic levels. This principle explains why spacecraft capsules and hypersonic glide vehicles have rounded noses rather than sharp tips. By controlling shockwave standoff distance, engineers reduce peak thermal loads by hundreds of degrees. It is a classic example of using physics itself as part of the thermal protection system. Hypersonic missiles operating inside the atmosphere encounter similar, though usually less extreme, conditions. At Mach 10, surface temperatures exceed 2000 A circumflex degrees C. At Mach 15, temperatures approach 3500 A circumflex degrees C. While these values are lower than orbital re-entry, they persist for longer durations because the vehicle remains within dense air. This sustained heating places enormous demands on materials and cooling systems. Some advanced concepts explore active cooling, where fuel circulates through channels beneath the surface to absorb heat before being burned in engines. Others investigate transpiration cooling, where small amounts of gas are released through porous surfaces to form protective boundary layers. These techniques borrow directly from rocket engine design and are now being adapted for hypersonic flight. Another frontier is plasma manipulation. Researchers are studying electromagnetic fields that could reshape shockwaves or redirect ionized air away from vehicle surfaces. If successful, this could dramatically reduce heating and drag. These ideas remain experimental, but laboratory tests have already demonstrated small-scale plasma flow control. Re-entry physics also reveals why atmospheric flight and spaceflight are becoming increasingly connected. Vehicles that operate at Mach 15 or higher begin experiencing conditions nearly identical to spacecraft returning from orbit. This is driving the development of hybrid aerospace systems that blur the line between aircraft and spacecraft. Future platforms may accelerate horizontally, climb into the upper atmosphere, coast at hypersonic speed, and descend thousands of kilometers away, all in a single continuous flight. This convergence of air and space engineering is one of the most important technological trends of the 21st century. Hypersonic research feeds directly into reusable spaceplanes, rapid global transport, and next-generation launch systems. The same thermal protection strategies developed for missiles and glide vehicles are now being adapted for orbital vehicles and commercial spacecraft. The broader implication is that humanity is learning to operate routinely inside extreme velocity environments. For thousands of years, transportation was limited to speeds below a few hundred kilometers per hour. In less than a century, we progressed from propellers to jets to orbital spacecraft. Hypersonics represent the next phase of this progression, where atmospheric travel approaches spaceflight in both speed and complexity. What makes this moment unique is the role of artificial intelligence. Modern hypersonic design relies heavily on AI-driven simulations. Neural networks analyze billions of fluid dynamics data points to optimize shapes, predict heat flow, and identify structural weaknesses. Designs that once took years to refine can now be evaluated in weeks. AI is not just assisting engineers, it is reshaping aerospace development itself. Re-entry physics teaches us that speed is never free. Every increase in velocity multiplies heat, stress, and complexity. Mastering hypersonic environments requires breakthroughs in materials science, computational modeling, control theory, and manufacturing precision. It demands cooperation between physicists, chemists, mechanical engineers, and computer scientists. It represents one of the most interdisciplinary challenges ever undertaken, and yet, this challenge is already producing results. Reusable spacecraft now land autonomously. Hypersonic vehicles sustain controlled flight for minutes at extreme temperatures. Advanced ceramics survive conditions once thought impossible. Each achievement pushes humanity closer to routine access to both near space and global hypersonic travel. But here is the deeper insight. Re-entry heat reaching 7,000 A circumflex degrees C is not merely a technical obstacle. It is a reminder of how much energy is contained in motion itself. Velocity is stored power. When released, It reshapes matter, ionizes air, and forces innovation. Hypersonic technology is teaching us how to harness that energy safely and predictably. Missiles may be the most visible application today, but the physics extends far beyond defense. The same principles will enable future spaceplanes, ultra-fast cargo transport, and perhaps even point-to-point passenger travel across the planet in under an hour. Re-entry science is quietly laying the foundation for an entirely new transportation paradigm. And this brings us to the real takeaway. Hypersonic systems are not just changing warfare. They are redefining how humans interact with Earth's atmosphere. They mark the beginning of an era where air and space are no longer separate domains, but parts of the single continuous operating environment. If you want to explore how future spaceplanes could use re-entry physics for global travel, how AI is already designing thermal shields autonomously, and how atmospheric plasma might one day be actively controlled, stay with the series. Because next, we dive into how artificial intelligence and hypersonic engineering are merging into one unified system and why that fusion may transform aerospace forever.